Wait, before you run down into the comments, let me make this clear that the purpose of this video is to educate those who want to know about how geologists have dated Earth and how we date rocks on Earth. And the purpose of this video is not to offend anybody or anybody's beliefs in any way. That is never my purpose or my intent. So please do not feel obligated to go into the comments and tell me what I should believe, because I'm not trying to tell you what you should believe. I'm just trying to educate here. With that being said, if you would like to know about how geologists have dated Earth, that is what we'll be talking about in this video. Specifically, how absolute or radiometric or isotopic dating works. All of those things mean the same thing. How we dated Earth or estimated Earth's age before we had absolute dating techniques, and why many of those estimates were very far off. How we finally got the correct age of 4.55 billion years. The difference between dating Earth and dating the universe, and ways that we corroborate our final estimate of Earth's age at 4.55 billion years. So first, like I mentioned, we're going to talk about what absolute dating is, but to talk about absolute dating, I feel I should mention what relative dating is first, because we used relative dating of rocks before we actually got to use absolute dating, because we didn't know how to use the isotopes correctly, or really what isotopes were. And so for a long time, we used what's called relative dating, which is exactly what it sounds like. It's dating the rocks relative to each other. So for example, in this cross section here, we have rock layers in, bright different colors. They don't look like that in real life, but that's what this figure is showing. And we can order these rock layers. That's what all these numbers are. And so basically we know 1 is older than 2 because it's below it and it was therefore deposited first. And then 3 is, above 2, so it's younger than 2, and so on and so on. And then there's some anomalies where we have intrusions of igneous material, and those are younger than the things that they're intruding into. We know that because they cut across the layers of the previously deposited sedimentary rocks, and that is called the principle of cross-cutting relationships. Now, I'm not going to get into all of this relative dating stuff. I have a whole video about these principles and how to use them to relatively date rocks. I'll link it up to the top right for you. But in general, this is kind of the way that we date rocks relative to each other. So strata or layers of rocks, we can date them relative to each other, or say this one's older than this one. Now, this is important that we remember that this is qualitative or relative. It's not numeric, whereas absolute dating is quantitative, is numeric. We can actually get a numeric age because we're using isotopic decay or radioactive decay to calculate the age of the rock. So the way that absolute dating works is kind of summarized in this figure. You have radioactive isotopes that form in the original rock, and then these decay over time, and because they decay at a constant rate, we can then come in and measure the ratio of red to blue, or parent to daughter isotope. The daughter, the blue, is what it decays into, and that's a stable product, so it remains the same over time. And so we can measure that ratio and then calculate how many years have passed. So let me kind of go through this step by step, how this works, because not everybody knows what an isotope is, for example. So what is an isotope? Well, first off, let's look at the periodic table. We have all these numbers at the top of it. What do they mean? Well, these numbers are the atomic number of the element, and the atomic number represents the number of protons. The number of protons defines the element. If that number changes, the element changes. For example, 6 is the atomic number of carbon. If that becomes 5 or 7, it becomes boron or nitrogen. It is no longer carbon if the number of protons changes. However, the nucleus of atoms, or the nuclei of atoms, contain both protons and neutrons. So what happens if the number of neutrons changes? Well, if the number of neutrons changes, the element is still carbon, but it is a different isotope. So the element is the same, but the isotope changes if the number of neutrons changes. For example, there are three naturally occurring isotopes of carbon, carbon-12 with 6 protons, 6 neutrons. That's why we call it carbon-12, because 6 plus 6 is 12. We have carbon-13 with 1 extra neutron, but again, the proton number is the same. That's why we can still call it carbon. And then we have carbon-14, which has 2 extra neutrons. And so 8 neutrons, 6 protons adds up to 14, 7 neutrons, 6 protons adds up to 13. You get the picture. But what's important about these isotopes is they can be unstable or radioactive and therefore undergo what we call radioactive decay over time, in which they undergo decay to become more stable. And so they release some sort of energy when they undergo decay, and then they become something else. In the case of carbon-14, it decays into nitrogen-14. The reason it changes from carbon into nitrogen is because the proton number goes to 7 instead of 6. And the reason for that is because one of the neutrons changes into a proton by releasing a beta particle or a negatively charged particle that made it neutral to become positive. Now, none of the types of decay here really matter. The point here is that there are isotopes that are radioactive and undergo decay. There are also isotopes that are stable, such as carbon-13 and 12, that do not decay. Now, I'm going to have a video coming out here soon about the difference between stable and radioactive isotopes and their applications. And so it's important to remember that radioactive isotopes, yes, are useful for dating, but stable isotopes are also really useful in other ways and other applications. So I'll talk about that in that video. But let's talk a little bit about how we can use these radioactive isotopes to date rocks. So isotopes decay at a constant rate. This is called the half-life. This is the amount of time it takes for half the parent isotope, in the example we just gave, that would be carbon-14, the radioactive isotope, to decay into its daughter product. For the carbon-14 example, that would be nitrogen-14. So if we look at the figure at the bottom of the slide, we see the red isotopes are the parent isotope. We can use the example of carbon-14. The green ones are the daughter, or nitrogen-14 in this case. Before any half-lives have passed, right as the rock had just formed, it has all parent isotopes or original isotopes, all carbon-14. By the time one half-life has passed, half of those parent carbon-14 isotopes have decayed into nitrogen-14, the daughter product. And if another half-life goes by, half of those red ones that are still left, that are remaining, will then decay into the daughter product again, and then it'll half again and half again after each half-life. We can actually look at this numerically on a graph, for example. This graph is showing the percent of carbon-14 or parent isotope remaining over the number of half-lives that have passed. So before any half-lives have passed, you have 10 grams or 100% carbon-14. After one half-life has passed, you have 5 grams or 50% of the original carbon-14. And then after 2 half-lives, you have 2.5 grams or 25%, because that 50 halves into 25. And then after 3 half-lives, you have 1.25 grams or 12.5%. Again, it halved at 25, and so on until the concentration of the parent isotope is negligible. And the reason that we can use the number of half-lives that have gone by to calculate the number of years that have gone by is because we know the amount of years in the half-life for that particular isotope decay system. For example, for carbon-14, its half-life is 5,730 years. But as you'll see in this slide, that is relatively short compared to other isotope systems. For example, other common radioactive isotope systems that we use for geochronology or for dating rocks include potassium-argon dating, uranium-lead dating, and rubidium-strontium dating, and these half-lives are in the billion-year range. And I should point out here that it's okay if Earth isn't old enough for that half-life to have passed yet, because we don't have to have a rock that's undergone a full half-life yet. We can have a fraction of a half-life, and we can still calculate how many years have gone by calculating the fraction of the half-life that has gone by. So the gist of radiometric dating is we measure the ratio of parent to daughter isotope in the final rock, however old it is, and that will tell us how many half-lives and therefore how many years have gone by. Note, however, that some isotopes have relatively short half-lives, such as carbon-14. This is only about 5,000, 6,000 years, so this limits the age of rocks that can be dated using that method. For example, for carbon, it limits it to about 50,000 years. Anything that's older than 50,000 years cannot reliably be dated by carbon dating. That's because by then, pretty much all the carbon has disappeared and become nitrogen, so you could not get a ratio. I find this point very important because a lot of people think that carbon dating is how we date rocks. I always get questions, oh, did we date Earth with carbon dating? No, Earth is billions of years old. Carbon decays way too fast. Nobody understands that there are other dating methods out there, and they think that we date everything with carbon dating, but we have so many different dating methods. I'll show you later just how many we've developed that we can cross-check on these same samples to double-check and triple-check and quadruple-check our work and our estimates. Now to get to how we dated Earth using radiometric dating. But before we talk about how we use radiometric dating to get 4.55 billion years, I should mention, well, a couple things. First off, this geologic timescale here on the slide has, numbers next to it that indicate how many millions of years ago each of these periods in Earth's history occurred. However, this timescale was originally built based on fossils, relative dating, not absolute dating. So originally we had this time scale here that was relatively, very similar with all the same periods and such with very similar boundaries, but it just lacked the numbers. We hadn't numerically assigned those periods, but we could assign those periods without the numbers because we could go in the rock record, for example, at the late Cretaceous or the Cretaceous-Paleogene boundary and see that there was a major extinction by looking through the fossils at that time. So we could call that a boundary and say there was an extinction event at the end of the Cretaceous, and that's when the dinosaurs disappeared or whatever. We can say these things without needing numbers. So that's what we did early on. And then when we had radiometric dating, we went back to all of those rocks and we dated them radiometrically. That's how we got the numbers. I should also mention that early on, before radiometric dating was a thing, many geologists had tried to make estimates for Earth's age. Radiometric dating finally then provided us the accurate and precise age of 4.55 billion years, but first we'll discuss the early approaches and the early estimates. So the first approach I'll talk about is how early geologists basically tried to calculate how long it took for our modern ocean to gain its salt content, its current salinity. And the way they did this is measuring the volume of river input, how saline the river input was, the rate at which it was coming in, evaporation rates that concentrated salinity, and all of these things. And they ended up getting an age estimate of basically how long it took for the ocean to gain its salt content of 90 million years. However, they miss a key point here. They forgot to take into consideration salt lost from deposition, which is a major component of salt that is lost from the ocean. Because salt not only precipitates as NaCl, but also, its ions in the water, its dissolved ions, react with so many other things to precipitate out as other rocks and become deposited. And so much salt content has been lost from the ocean. It's not just going in, it's also being deposited. And so because this was a huge consideration that they completely missed, that's why this estimate was way too young. They were only considering input and not output. Another estimate that was much too young was made in the 1860s, in which Lord Kelvin calculated how long molten Earth should have taken to cool to its present temperature, and the age estimate was around 100 million years. Again, much too young because he didn't take into consideration all the heat sources. This was not his fault. We actually hadn't discovered yet these other heat sources such as convection and, ironically, radioactive decay, which once we discovered it, not only helped us understand that it was an additional heat source, but also led to our radiometric dating technique. So I find it ironic that this thing we hadn't discovered yet was a heat source that would have helped this age estimate be more accurate, but also ended up being the thing that we used to date rocks on Earth. So in any case, these young age estimates of around 100 million years really troubled geologists and biologists because geological and biological processes such as deposition, mountain building events, plate tectonics, which hadn't even been discovered yet, evolution through natural selection, all of these processes take much, much more time. And so geologists had, of the processes that they had discovered at the time, seen that those processes would have required way more than 100 million years to get to Earth's current state. And biologists also saw the same thing in terms of to get to life's current state. In 1856 and 1892, around the same time that Lord Kelvin was making his estimates, there were other scientists that also made calculations or estimates of Earth's age, which were both around 20 million years. And both of these estimates were based on the sun. These scientists calculated how long it would have taken for the sun to condense to its current diameter and brightness level from the early solar nebula that it accreted from. However, their assumptions were off, once again, leading to a much younger age than it should have been because they assumed the sun was only heated by gravitational contraction, and nobody yet had discovered solar nuclear fusion, which is like one of the main drivers of the sun's heat and brightness. George Darwin, Charles Darwin's son, also made a stab at an age estimate for Earth. He proposed that the Earth and Moon broke apart early on when they were both molten and calculated the amount of time required for tidal friction to give Earth its current 24-hour day. Now, just a little background here. The moon formed from a major impact with Earth very early on, around 4.5 billion years ago, and then accreted from material that then orbited Earth. And ever since then, the moon has been tidally pulling on Earth, and it's been steadily moving slightly further and further from Earth, and as it does so, it makes Earth's days longer. So he calculated how long it would have taken to get to 24-hour days, and he got about 56 million years for his age estimate of Earth. But it wasn't until around 1895 that John Perry actually challenged these young age estimates based on conductivity and got an estimate of around 2 to 3 billion years old. This is the closest that we've come, but his work was largely ignored, which is so sad. Finally, we learned about radioactive decay and how radioactive decay provided heat to Earth. And so in 1903, George Darwin, Charles Darwin's son, and John Jolly pointed out that the assumption that Earth and the sun's heat had been steadily dissipating into space was not fully correct because it also had been continuously replenished by radioactive decay. Finally, once we determined that these isotopes decayed at a constant rate, the concept of the half-life was born. Then in 1907, Bertram Boltwood radiometrically dated 26 rock samples, getting age estimates of around 400 million to 2.2 billion years of age, which was major because that showed that there were rocks on Earth that were 2+ billion years old that negated the early age estimates. Even the ones on the younger side of this range negated the early age estimates that other scientists had made. Now, these techniques were not perfected, so they definitely had their flaws, and these age estimates weren't perfect early on, but they were much closer to Earth's actual age than the early estimates based on salt content and heating were. In 1911 to 13, Arthur Holmes dated many rocks over 1 billion years old, but radiometric dating in the geological community really didn't gain trust until later in the 1920s and 30s. One reason that it started to gain trust was Joseph Barrell's research showing that strata, or layers of rock, had not deposited all at the same rate, and so we really couldn't trust the rate of geologic processes to estimate Earth's age. We had to do it some other way, and so his research pushed geologists in the direction of radiometric dating. And then in 1921, scientists at the British Association of Advancement for Science agreed that the Earth was around a few billion years old. Now, this was with huge error bars. They were just kind of estimating based on some of the radiometric dates early on. And they then agreed that radiometric dating was credible, which was huge because then a bunch of geoscientists got into it and made the techniques more reliable, more accurate, more precise. Arthur Holmes then went on to publish The Age of Earth, an Introduction to Geological Ideas in 1927, giving an estimate for Earth's age of around 1.6 to 3 billion years old. These are still huge error bars, but they were becoming way closer to their actual age of Earth. And these early radiometric estimates of Earth's age and just dating in general with radiometric techniques was really, really impressive because it wasn't until the 1930s that isotopes were really even slightly understood. Before then, we didn't even know that isotopes had a different number of neutrons, and that's what was causing their decay and like all of this stuff. We didn't know what they were. So it's even more impressive that we were doing this before we understood the process of radioactive decay. Since the 1960s, radiometric dating techniques have been fine-tuned, and now we have over 40 different techniques or isotope systems that we can use to date rocks, and we often cross-check dates using many different techniques on the same sample and make sure they're in close agreement. If they aren't, we investigate and typically find the reason to be contamination, and now we have fine-tuned sample prep techniques, sample preparation, to minimize contamination and get the most accurate dates. And so now most of the time when we cross-check the same sample with different dating techniques, we get a very close agreement. So moving on, now we know that radiometric dating works. Now we know how to use it. So what do we use it on? How do we actually get the age of Earth? What rocks do we choose? How do we know what's oldest? Well, let's talk a little bit about Earth rocks and what's oldest on Earth. So we have oceanic crust and we have continental crust. The oldest oceanic crust is only about 260 million years old because it's constantly recycled or subducted at subduction zones where it gets recycled back into the mantle, unfortunately. So continental crust is much more promising in terms of finding older rocks because it's preserved for a lot longer because it's too buoyant to subduct, so it typically stays at the surface and does not become recycled into the mantle. However, even the oldest continental crust is only about 4 billion years old for the oldest rock estimate and 4.4 billion years old for the oldest zircon grain estimate, and that does not represent 4.55 billion years old. So why is this? Well, continental crust didn't actually form right when Earth was accreting, right when Earth was being born, basically. Earth was molten and had to cool a bit before continental crust could cool and, isotopes could set, basically. So I'll talk about this in a future crustal formation video where I talk about how oceanic and continental crust eventually formed on early Earth. So this brings us to how did we finally get that 4.55 billion year old age estimate? So this comes from our understanding of the solar system and how planets, moons, asteroids, comets, all the bodies in our solar system accreted during the solar system's formation. So therefore, we can use radiometric ages of meteorites to estimate the age of not only the solar system, but all that it contains, the planets, the moons, and everything. And so all of the meteorite ages give us 4.55 billion years in age. And so that is where we get that. But again, why is it that we have to use meteorites and not Earth rock? Why doesn't Earth rock give us these ages? Well, Earth rocks, again, are not only not old enough, but also most Earth rocks that are very old have undergone alteration, whether it be metamorphism or some type of, heating or something that has either partially or completely remelted and recrystallized that rock. And whenever you have remelting or recrystallization, isotopes are reset. So the rock that you're dating, you're actually dating the alteration or the recrystallization date, not the original date or age of the rock. The first time that meteorites were used to get this 4.55 billion year estimate was by Claire Patterson when he dated several meteorites in 1956 using uranium-lead radiometric dating techniques, which were then corroborated and cross-checked using other dating techniques. And so here's a few different meteorites that we've dated using uranium-lead, samarium-neodymium dating, rubidium-strontium dating, rhenium-osmium dating, and argon-argon dating. All of these techniques give us a very close estimate of 4.55 billion years old. So these are very consistent because meteorites represent the age of the solar system. They are small bodies that accreted when the solar system was forming, and because they didn't accrete onto a larger body, they just stayed small, and because they never, underwent any secondary recrystallization or remelting events, we can use those to date the solar system. Now, briefly here, I want to mention the difference between dating Earth and dating the universe. The age of the universe is based on light, basically, the speed of light. So we use the light stretching, or what's called redshift, to understand the distance of an object that we're receiving light from, that we're measuring with our telescopes, or whatever it may be. And then we use the speed of light, which is a constant, 3.0 times 10 to the 8th meters per second, or 2.999 or something like that, to determine how long it took for that light from that object to reach Earth. So then we can measure the rate of expansion of the universe and kind of work backwards to the Big Bang, or the birth of the universe, to get an estimate of the amount of time required for the universe to be at its current state. And the amount of time required to do this we estimate as 13.8 billion years. But getting back to Earth, because that is the point of this video, as I am Geo girl, not universe girl. So we can corroborate this age of 4.55 billion years, not only by using, other meteorites, because they are remarkably consistent, but also using the absolute and relative ages of other rocks around the world, as well as throughout geologic time. So both temporally and spatially differentiated rocks we can use to basically paint a continuous picture of Earth's history, which corroborates the 4.55 billion years, because we can see that it took, this amount of time for all of the major events on Earth to occur. And so what is this continuous picture of Earth history? Well, for that, you can check out my historical geology playlist, which should pop up here at the bottom of the screen at any point now. If you want to check out the major references I'm using for this video, they're linked in the description box down below. And if you want to check out other related videos, you can see the difference between stable and radioactive isotopes, which will pop up here any second, as well as the crustal formation video, which should also pop up here if I've filmed it by now. And with that, guys, thank you guys so much for watching, and I'll see you in the next video. Bye.